All right, well, hello and welcome to the next episode of 3D and 30. Today, we're going to continue our technical series, which we started with the non-contact recoder. If you're interested in seeing that one, we can send you a link to that, maybe in the notes here. Today, we're going to talk about Height Mapper, which kind of continues the non-contact recoder story. It's sort of like the next chapter of it. And I think this is a good one to go into. Last week, we had our Velo3D Summit, which is our big headquarters show. We invited a number of VIP customers and prospects to come and join us. And it gives us a chance to talk to our engineers directly, one-on-one. And one of the things I like to do when I go to headquarters is talk to our applications engineering team about what makes a build successful. This is one of the most challenging things to get right in additive manufacturing, and it's complicated. So, what are the rules in setting up builds, and how do we go about doing that? Most often the answer is it depends. And obviously that's not what you want to hear. You want to kind of get to the bottom of it. But at the bottom of it, they're dealing with a lot of different variables, and it truly does come down to what the part looks like and how those variables play a role in printing that part successfully. So how do they get quickly through it? Maybe the first one is a little bit more tricky, and maybe the first one, it does depend. How do they learn as quickly as they learn in order to make the next one successful, or maybe the third one? And it turns out it's not any kind of post-processing inspection. It's not an NDT or non-destructive test. It turns out that the most common answer I get from our applications engineering team is Height Mapper. So Height Mapper is quickly rising to the surface as one of the most powerful diagnostic tools to ensure that the build is set up properly. And if you're going to use my words, I want to know how to bulletproof a build. They're not going to say that because they're engineers. But essentially, if you're going to bulletproof your build, you're going to want to use Height Mapper, and you need to understand how to use it. So what is it? How do you use it? And why is it important? So on this episode of 3D and 30, we're going to bring back Michael Harsh, our technical sales of EMEA Central, to talk about his experiences with Height Mapper. He's one of the foremost experts in using it, and how it helps him set up builds. Again, my name is Mike Rogerson. I do product marketing for Velo3D, and we're excited to have you here. As a reminder, this is a live show. We love to get questions. They do have a little bit of a delay between when you ask the question and when we actually receive it. So give us that delay, and then we'll look for opportunities kind of in our narrative to get to the question, but we do like to get to them as quickly as possible. So please send in your questions as soon as you want. All right, well, Michael, welcome back to the show. So how have things been? Can you remind us of your background and kind of where you are now and what's going on?
Yeah, thanks for having me here again. Yeah, I've been in the LPBF industry on the application side for quite a while. I think almost 7 years now. And I believe in the end of January, that would mark my 2-year anniversary with Velo3D. And yeah, it's been very exciting. Yeah, specifically with some of the features that the Velo3D AM solution offers on the hardware side and on the process side. And as you said, Height Mapper is a key component here. And yeah, I hope we can shed some light on that significant piece of hardware.
And so I kind of brought up the idea that some of the engineers I've talked to at headquarters, in their one of the most critical tools to diagnosing builds. Do you share that opinion? Or are you kind of in the same school of thought there?
Yeah, definitely. So in Velo3D, we really try to target these applications that, yeah, historically make trouble on legacy LPBF systems. And yeah, with Height Mapper, it's really a great tool to give us some data on what works and what does not work, and how we can optimize a process or a build setup to get it to work.
So, well, let's kind of walk through this a little bit. Maybe you're working on some projects now, or you can sort of think of a project you've had before without giving us anything that you can't share publicly. How do you use Height Mapper? Can you walk us through that?
Yeah. So, well, let's talk about how we use it during a build. And actually, there is a project right now that, well, where it turns out that Height Mapper was incredibly useful to get this to work. It's from a larger compressor company, and they threw some shrouded impellers at us that were quite large in diameter and very, very low on the downskin angle of the top shroud. Yeah, kind of like what you see here. And well, yeah, to get this to print or to see how far we can push our process, Height Mapper is really a great tool to monitor the build layer by layer when we start building or printing that top shroud and see if we are in the allowable process range.
And so you kind of mentioned that top shroud. This is an example that we looked at before, obviously different impeller. But walk us through what's happening here. This is a screenshot from Flow. We've kind of pulled up the Z axis to a certain point in time in the build. So this is what the printer would be trying to do as it builds layer by layer. This would be an example of one of those layers.
Exactly. So yeah, you have to imagine basically the process of printing that part is quite simple up until we get to the upper edge of that shroud, that perforated shroud around the outer circumference of the part. And from that point on, we are basically we are growing that shroud inwards and up. If the angle is lower, we are more biased towards growing it inward. If the angle is steeper, we are more biased growing it upward. And with each layer, basically the diameter of that leading edge is decreasing or getting smaller and smaller.
And maybe we take a little bit of a step back here. Not everybody's familiar with the process that we're using. We are using what's called LPBF. And I'll let you define what that acronym is. And what's unique about this process? Why has this become a challenge in LPBF?
Yeah, so LPBF stands for laser powder bed fusion. So we have a powder bed as the feedstock, so to say. We create that powder bed by laying down a very thin layer of that powder with a recoater. And then we use an energy source. The name says it, it's a laser, or in our case, actually multiple lasers. And we shoot these lasers into the powder bed. And in that process, you really have to understand that it's a melting process. So we turn the amorphous powder, solid powder, into a fully liquid state. We call that a melt pool. And yeah, when that melt pool solidifies, as soon as we turn off the laser source for a specific region, that melt pool turns into a solid. So it's kind of like creating a laser weld in the end. And that process by itself, or the physics of that process, mean that we create residual stress. And yeah, the most important point to understand here is that the residual stress comes from the change of the material from the liquidus to the solidus phase. So we have a liquid melt pool. That one contracts, gets smaller, the volume gets smaller because the density gets higher. And that contraction with the melt pool also being constrained to the previous layers and the surrounding already solidified material creates that stress. And that stress, depending on the geometric boundary conditions that we have, will lead to warpage of the part.
So in kind of going back to this, it just occurred to me that we've got this gray and we've got this orange. So, and the orange is properly colored, right? This is kind of the hot zone. This is what you're talking about. This is shrinking. You've got the gray zone, which has already been cooled down. It's presumably not really shrinking as much as the orange. So you've got a layer on top and a layer that's sort of stable. That layer on top is now trying to do something and compress itself.
Yeah. So maybe, yeah, let's explain a bit more what I meant by geometric boundary conditions. This is a good example. So I talked about the contraction of the melt pool, and I actually prepared a bunch of cards because I think it's a great way to show what's happening. So we have a single layer, and this is now our solidified material. And basically the residual stress that I talked about due to the melt pool contraction makes that layer want to warp like this. Now, if you go back to that picture with the downskin and the shroud, where we are still building that wall, all we are doing is basically stacking cards on top of each other. And in this situation, we are actually increasing the bending stiffness. So that is not a problem. The residual stress is not strong enough now to warp these multiple layers of cards, this set of melted layers on top of each other. However, as soon as we go into that top shroud, that downskin, what we're actually doing is now putting another card on top and offsetting it towards the shroud or the previous layer. And again, the lower the angle, the wider the lever is to the previous layers. And now you can imagine that previously mentioned effect will make the leading edge or the current layer that is growing inward and offset want to warp upwards. This is the problem we are facing. This is the fundamental problem of laser powder bed fusion, and why we cannot print everything that we would like to print as easily.
So in your card analogy, so I thought the cards are just going to fall over, but I guess in the metal analogy, they're actually warping up and kind of deflecting.
Exactly. I mean, basically, we always try to keep the leading edge connected to the previously printed and solidified geometry, so they are constrained on one end, but there is also an unconstrained edge, and this is the edge that wants to protrude upwards.
Okay. So we've got a layer by layer process. We kind of talked about that. We're building stress. That stress wants to sort of bend your cards, so to speak. How are you able to print anything then? Why isn't this just bending all over the place? How do you manage this?
Well, yeah, first of all, there is a, let's say, robust process window for the process. So if you have the right process parameters, or if you do a lot of DOE for a low angle downskin, you can actually get to a point where it prints somewhat nicely, but it's a lot of work, it's a lot of effort. And then I guess the key word would be DFAM. I mean, DFAM has been preached in the LPBF industry over the past 15, 20 years maybe. And this means either restricting the angle that you can print, so basically not offsetting the cards as much as possible, but limiting that offset, therefore limiting the angle, or implementing support strategies. So basically you put anchors underneath the surface of the card that is overhanging and counteracting the warpage that way. Basically, these anchors increase the bending stiffness of the leading edge. And for some
basically got $1 million staple gun, and you're using this staple gun to staple your metal part to a metal build plate at that point, huh?
Yeah, well, kind of like that. But the thing is, yeah, in some cases, for some applications, that's really not a problem if the support is accessible, if you have the freedom to change geometry. But as previously mentioned, on turbo machinery, these impeller types where you really want to design them for maximum performance, and you also cannot necessarily access the area between the vanes and shrouds, then yeah, you are basically out of options and cannot print it.
Okay, so like what you've got now with your protrusions, and you're trying to anchor them down. I mean, is there sort of a limit? Are there some protrusions that are okay, or you know, why are they problematic? What's it actually causing to happen other than the deformation?
Yeah, for LPBF systems that use a standard recoater, so just a blade with a very, very low clearance, or let's say a blade where the clearance of the blade is the layer thickness you want to create, 50 microns, 40 microns, 100 microns, you have your answer there. So if the clearance is 50 microns, the allowable protrusion would be 50 microns. Otherwise, if you do the next recoat, you would hit your part, hopefully maybe only deflecting the part slightly, but in most cases it's a catastrophic build failure that could even lead to damage of the system.
And so the recoater is going to hit that metal part. Now, which is stronger? Is recoater break in that case? Is the part break, or does it depends? That's the answer, right?
It depends on the part in the end. Some high aspect ratio features that are very thin and tall, they may just bend. In many other cases, like on the impeller, I would say your recoater is going to give. And either way, it's a catastrophic build failure. You cannot continue like that.
Okay. And last time we kind of talked about the non-contact recoater. So I bet that changes things.
Exactly. So the key takeaway is that on our recoater system, we do not have that restriction of allowable protrusion equals distance from or working layer thickness, because on our recoater system, we are able to achieve a much higher clearance. We talked about that in the last 3D in 30. It's really worth a watch. But basically, we have 3 components of the recoater that have all a very high clearance, basically more or less more than a millimeter. And therefore, our allowable protrusion is much, much higher, like 20 times higher than on LPBF systems that use a blade type or roller type recoater.
Okay. And so you've got the height mapper. Does it work with the non-contact recoater?
Yes. So the height mapper basically covers 2 functions. So first of all, when we are printing, we want to be able to monitor the protrusion. Yes. Yeah, exactly like that. This is actually a picture or a bunch of pictures that we record during the build after each recoat and after each lasing operation or laser emission has completed. And then we basically want to see what the powder bed roughness is. So how is the quality of the powder bed? And do we see any excessive protrusion of the part after the lasing is completed? And maybe if you bring back that picture on the bottom right picture, that little cone on the bottom right, you can see obviously something here is going wrong. We have some excessive protrusion, and this is the data we are looking for. This is the data that helps us, first of all, understand if our process works correctly, and second of all, if the allowable protrusion is within the limit of our process. So basically between 0 and 800, 900 microns, depending on the material.
Yeah, we've got another example, but there's a kind of this gray image and this green image. And can you sort of give us an example of what the difference between the two?
Yeah, so we have a high resolution camera that initially takes that raw image data, that photo you see at the top. And then we do have some image processing in the background that creates basically a color map. And based on the color of the pixels that we see here, we have some information about the protrusion height.
So it's kind of like a topography, like you see the mountains of Earth, or I guess for
exactly.
Europe.
Yeah, imagine a topographic map.
Yeah. Okay.
Yeah,
that's pretty useful. So now you know the height and you know the protrusions. So what happens if you raise that bar? Like you mentioned, 50 microns is the limit for traditional printers. Now you've got 200 microns potentially without an issue, or maybe more. But like, what does that do then? How does that help?
Yeah. So I talked about the robust process window for LPBF. If the robust process window is like this, and let's say here the upper limit is the allowable amount of protrusion you can achieve, 50 micron on a standard LPBF system, and suddenly you have the capability to raise that, your process window gets much larger, and it allows you to play with your process parameters. I cannot go into detail as much, but basically the height mapper together with the non-contact recoater is a facilitator for some very unique processes that we use in these low angle downskin regions.
And how often are you looking at the height mapper images?
Well, less and less over time, because with every build that we do, we collect a lot of data. We know what works and what doesn't work. And only in that case that I mentioned in the beginning, where we get a part, we get a CAD model where we already know that is kind of on the edge of where we know it works. This is where the height mapper data is really, really useful to validate that your process is stable or stable enough, or whether you need to do some tweaks to the process or the build layout to make it work.
Well, I guess I meant, like, how often does the system take an image? not you specifically, but how often does the system look at it?
Every layer. So we document the entire build process. That's actually also really useful to the end customer to understand or to prove, here, this is the data layer by layer, after recoat, after lasing. We can tell you for any layer of the build how the powder bed quality was and how the protrusion tendency of the part after the laser emission was. And if you give that to a customer, that creates a high level of confidence in the quality of the process.
Okay, so just to kind of reiterate a couple things, it sounds like we've got grayscale image, which is just a camera. That's a high resolution camera that you mentioned. Then you've got these green maps, which are the topographical maps where you're looking at the height. And I see 3 of them. Is it just taking 3 different images, or what are these 3?
Well, it's just, so it says recoat, quality image, and lased height map. And basically the ones on the left reflect the powder bed. So after the recoat is completed, but before the laser has started emitting. And the lased height map shows the powder bed, including the solidified parts after laser emission is finished.
Okay, so it's taking a lot of images every layer then. So
yeah.
It sounds like you've got one after the recoating, and then you've got another one after the lasing, and then after the recoating, after lasing. So you've got multiple images every single layer now.
Yeah, no, it's a lot of data. But yeah, if you use that data, it helps you learn quickly. And as I said, LPBF is still a young technology, even though what we can do with regards to mechanical properties to part quality is much, much better than what you see on the best casting parts. But having that amount of data just accelerates acceptance of the technology and industrializing, scaling it for serial production.
Okay, and then that's what's being plotted here, where you've got the, I guess, peak height for every one of those layers. You're plotting this for thousands of layers. Like, I mean, this could be 10,000 layers on a very tall part.
Yes.
Where you've got all this data now compiled.
Exactly. But in the end, the graph is really useful, because before I look at individual pictures, I just look at the entire graph. I see if there are outliers, like the one that you see here that's just above the warning threshold. Warning threshold doesn't mean it's critical. We still have basically twice that clearance above. But then I could pick that data point and look at the images and see exactly what happened.
So, I mean, I get how you can look at protrusions. That seems pretty clear. Are you able to use this for anything else? It seems like it's a pretty powerful tool that maybe smart engineer would figure out another trick with it. Are there other things you can do with height mapper?
So first of all, the recoater with the 3 components, basically dispensing, blading, and vacuuming powder. All of these, or these 3 operations, need to be validated or quantified as well. So what we actually do for the Recoater setup is basically doing a Recoater movement where we only dispense powder. We take a picture, get our topographic map, and see if the valleys and hills of the powder, exactly like that, are within spec. And then we repeat that for the blade, and we repeat that for the vacuum. And this is how we can set up the Recoater very consistently and within the allowable range. And there's actually another very interesting feature that not many people know about. We have to talk about our inert gas flow in the chamber, because if you think about how it's typically done on LPBF systems, you have, and I've done that myself in the past on other systems, you have your engineer coming in and then setting up some flow measurement device, pitot probes in different places across the build chamber. That by itself is quite complicated, and you need to get it right to measure the speed of the inert gas flow. But the problem is the pitot probe or the measurement device itself, when it's in the chamber, will interfere with the inert gas flow. So how accurate is your measurement then? And what we do is a completely different approach. We don't actually care about the flow speed in the chamber. We don't look at that directly. What we do is we have a flow rate measurement in the pipe before it goes into the chamber. We know the mass flow or the flow speed there. And all we do is make a recoat, powder bed, take a picture, and then we let the inert gas flow run for a specified amount of time. And we take another picture and we compare the two, basically to see if erosion in the powder bed happens. So erosion means the inert gas flow is too fast and it's basically moving powder away outside of the chamber, basically changing the layer thickness. And if we are not within that limit, or if we are not seeing that, we know that we can increase our pump speed, our inlet gas flow, until we just hit that threshold where we get the fastest possible inert gas flow while not eroding the powder bed.
Okay, so you've got, I think you mentioned 3. So it helps you set up the non-contact recoater and validate that that's doing all of its 3 steps right. You've got layer by layer, but not just layer by layer. It's like twice every layer.
Yeah.
So I guess by layer. And then you've got gas flow set up. It sounds like a pretty powerful tool that's built into this system. Is this coming at additional cost, or how do you get this if you want this?
No, it's a standard piece of equipment that is on all our Sapphire and Sapphire XC systems. The cool thing is that the whole measurement really doesn't take a lot of time. So basically, as soon as the recoater has went back into the standby position, has reached the standby position, it's just a flash of light where we use our projector to basically project the pattern that we use for height map measurement onto the powder bed. And it takes less than a second.
So just like taking a picture, it's just how fast does it take to take a picture? It's pretty quick. Yeah.
Yes, and while the image processing is happening, which only takes a couple seconds, the laser is already going, or the main process is already continuing. So the image processing is happening in parallel and does not actually slow down the process.
So you mentioned that you had some experience working with other systems. Can you kind of compare what it's like on another system without this height mapper compared to a Sapphire with height mapper? Like, what would you say are the biggest takeaways there?
Well, the main takeaway would be that if you don't have any protrusion monitoring at all, you are always gambling if you're doing a challenging part that you may have not done before, or that is pushing the boundaries, that you will fail the build or damage your machine. And that's the most critical thing here. If you have a machine that can avoid collisions due to these protrusion events, that's a huge game changer. That saves so much trouble, so much time, so much resources, and in the end will just increase the availability of your system.
So you don't want to have a broken $1 million staple gun.
Yeah, exactly.
Make sure your staple gun is up and running. Well, that's also, I do want to allow, if there are any questions, I did scan a couple times here. It looks like folks are reaching out and saying hello, and that's pretty awesome. If anyone has a question really quickly, we are up at 30 minutes right now, but I'll let Michael do some closing remarks. And then if I see something pop in, we've got probably enough time to sneak one in.
Yeah. So again, maybe to summarize, for me, the height mapper was probably one of the many reasons why I wanted to see what the Velo3D platform can do. And it really showed that the amount of data that you get to, on the one side, help calibrate your system, validate the powder bed quality, set up your recoater, and on the other hand, monitor and collect all the data throughout the process, basically expanding your knowledge by solid facts, by solid data points, and not just soft experience and soft guesswork, is really a game changer and has helped me on so many customer projects.
Nice. So hopefully we piqued your curiosity to learn more about Height Mapper. If you would like to continue learning more, we do have a white paper that we have released called Velo3D's Height Mapper Enhances the Landscape of Modern AM Metrology. You can click to download, or we'll probably embed a link in the channel so that you can download this. Obviously, it's not going to cost you anything, maybe an email address, and that's about it. But please, if you're curious, download this. It's a great resource. We have a lot of new technical content that we're working on publishing, and this will be another piece in that series. So if you're interested in learning more about any of the laser powder bed fusion technologies, or more specifically Velo3D's approach to this technology, great resource for you, and this will help answer a lot of your questions. So Michael, thank you for being on the show. Another great session. I love deep diving into technical topics with you. We'll probably have you on again eventually. So stay tuned for that. And audience, thank you for joining us. Looking forward to another show in a couple weeks. And that's all we've got. Happy Halloween if you celebrate that. Happy All Saints Day if you celebrate that. Happy late October if that's all you got.
Thanks, Mike.